All right. What we did last time, we talked about the basics of algebra, the basics of mathematics. It's the same in any math course you ever take, or any course that involves mathematics. So now we can start the chapters. A lot of the stuff we've done already on last week. The first section we have for homework assignments is chapter 1, section 8. It deals with exponents, roots, and order of operations. Well, we did one of those. We did order of operations last week. So today we're going to start talking about exponents and roots. What is an exponent? What's another name for an exponent? What does an exponent look like? Give me an example of an exponent. Oh, so PEMDAS, okay. Ah, yes, a number, say 5. If it's squared, if it's raised, so that number there is our exponent. Another name for it, it's also known as the power. So this equation here is read 5 raised to the power 2. Like I said last time, mathematics is language. We have to deal with a bunch of words here. So once we understand the words, the operations are pretty easy. So we notice that this is the operation for exponent. Now, both of these numbers have names. This we already determined is called the exponent or power. It's raised to the power 2. Can anybody guess what this bottom number is called? Base. It's called the base. Now, what would that be equal to? Yeah, 15. How do we get 15 so fast? Okay, we could. 3 plus 3 is 6. Plus 3 is 15. That's one way you could do it. This is using addition. Well, we can also use multiplication. It says the number 3 is repeated 5 times. The number 3 is repeated 5 times. Now, in that statement I just wrote there in English, the number 3 is repeated 5 times. This word here is not by happen chance. The number 3 is repeated 5 times, so it's the same thing as 5. In other words, it's 3 times 5. So a number that repeats itself that many number of times. So that equals 15. So we first start with addition, then we move to multiplication. So we take a long series of numbers that are added, the same numbers, and just multiply them instead. Then, what if we had this example? What would that equal? $81. Well, how'd you get 81? That's not what you did. Okay, but 3 times 3 is times 3 times 3. Well, yeah, see, but 27 times 3, you'd have to do some carrying and stuff like that. Remember what we talked about last week? The associative property. And the first one, the commutative property. I can associate these two together, and I can associate these two together. 3 times 3 is 9. 9 times 9 is 81. You notice how both of these answers came up to be the same, even though the numbers look different. Since all of these are multiplied together, we could have said we have the number 3 that repeats itself 4 times. That's what an exponent's all about. It tells us the number of times the base is multiplied to itself. Tells us the number of times the base is multiplied to itself. The exponent, the number on top, the power, tells us how many times does the base number repeat itself. The base number is 3. It repeats itself 4 times. 3 times 3 times 3 times 3. How would this one be written? Yeah, the base is 9. The number that repeats itself is 9. It repeats itself 2 times. And we see that both of these are equal. They're equal. So basically, just like multiplication is a way we can make a bunch of long additions shorter, that's what exponents does. It takes a bunch of long multiplications and makes it shorter. How would you write that as an exponent? Yeah, so what would be the base? What's the base? The base is 2. In other words, the number that repeats itself is, these are each of the bases. And the number of times it repeats itself that's your exponent. So it's 2. How many times repeat itself? 5. That's how you write exponents. Because this is equals, you have to be able to go both directions. If I give you 2 to the 5 and ask you to expand it, so you take the number 2 and write it 5 times. 1, 2, 3, 4, 5. Right, so that's what exponents all about. If I gave you this, ask you to expand, that's supposed to be a 2. If I give you that, ask you to expand it, how would you write it? So write it out. How many 2s do we got? Yeah, so it's 2 times 2 times 2 times 2. There's 4 2s. There's 4 of them, which is because of the exponent. Wow, this automatic focusing thing sucks. But how many A's do we got? Yeah, we have 3 of them. So it's times A times A times A. And how many B's? Is that? No, go have a seat. Have a seat. Apologies not necessary. Thank you, though. And that's how it would look if we expanded it. So you see the beauty of it, of using exponential numbers. Instead of writing this huge series of numbers and letters, we can condense it to this. Okay, how about this? Write that as x using exponents. When we read them out to you, I write them down. We could be confused. So it's A 3 B A C A 3 B A B B C C 3 A C. So how many letters are there? How many can you count up there? And I do apologize for that small postage stamp looking. I thought it was gonna be bigger on the screen, but it's pretty small. How many letters do we have? 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We're supposed to have 18 total, 18 elements, not just letters and numbers. So we have 18 members in our set. So how would you write it using exponents? Yes, sir. 1, 2, 3, 3 to the power 3. Very good. Power what? 4. Is that right? How can we check to make sure it's the right answer? That we're not leaving anything out. The first thing we can do, we know how many letters there are, how many elements there are, don't we? So if we take these numbers here and add them together, what do we get? 3 plus 7 is 10, plus 4 is 18. That tells us how many elements we have. We know that 3 of them are 3s, 7 of them are A's, 4 of them are B's and C's. So that's the way you can check to make sure your answer is going to be correct. If you're taking a large series of elements and condensing it. Yeah, so find the values of each of these numbers. Well, work these out. Tell me the answers. All 13 of them. All right, so let's look at these. 1 squared is what? 1. There's 1 times 1 is 1. 2 squared. 3 squared. 4 squared. 5 squared. 6 squared. 7 squared. 8 squared. 9 squared. 100 or 10 squared. 11 squared. 12 squared. 13 squared. And I'll show you shortcuts in the last 3. All right, these are important. These are all called they're called perfect squares. And you keep on going. 20 times 20, 40 times 40, 80 times 80, a million times a million. So any number multiplied to itself is a perfect square. Now, why is that important? Because the next part I'm going to show you all. The next part of this chapter deals with square roots. And I'm going to show you why they call it square root. I mean, the word root. Why square root? And I'll show you. The square root looks like this. Another name for that symbol is called a radical. So in mathematics, that's what we said. We're talking about radicals today. It means square roots. There's an invisible number there. This number in here is called the root. If there's nothing there, that means there's an invisible 2 in there. Hence, square root. So I'll put 9 in there. So how would you read that? It's a square root of 9. It's called the square root of 9. What is it asking you to find? It's asking you to find this. Okay, first off, because it's squared, what number is inside that V? 2. So it's asking us this. A square root is asking us to find any number that is multiplied to itself 2 times and equals 9. So that's what the square root's asking us to find. So it's asking us to find what number multiplied to itself 2 times gives you 9. Do we know what that is? Because 3 times 3 equals 9. Or more importantly, how can we rewrite this? So what we have here is this. The square root of 9 is the same thing as the square root of 3 squared. Is 3. well, I'll go one step further, is the same thing as 3 times 3, which is 3. That's the reason I asked you to find the perfect squares first. Remember the perfect squares? These? So if I asked you to find the square root of 64, what would you tell me? Why is it 8? Right, because 64 is made up of 8 times 8. So basically, the root tells us the number of times a number is repeated before it can be removed from the radical. The root tells us the number of times a number is repeated before it can be removed from the radical. That sounds like a lot of words, gibberish, but here's what it means. Since this is a square root, there's a number 2 here, right? So if I have a number, if I have the same element repeated twice, I can remove it, take it outside. How would you do this? Is the 16 giving you problems? We can separate all of these since they're multiplied. We can separate them since they're multiplied. They all multiply together. So what's the square root of 16? 4. Remember, the root tells us the number of times a number is repeated before it can be pulled out. So how many 2's do we got? We got 2 of them. Since we have 2 of them, that A can come out. And this one, we have B times B times B times B. Here's two of a kind. So that's a B. Here's two more of a kind. Because what I'm looking for are pairs of numbers. And there's your final answer. What does the root tell us? The root tells us the number of times a number has to be repeated before it can be taken out of the radical. What does that equal? What is it? It's 5. Why is it 5? Because 25 is made up of what? That's made up of 5 times 5. Since I needed two of a kind and I have two of a kind, it comes out. Make sense? So that's how each of these numbers here in this perfect square chart. If I take the square root of 100, it would equal what? 10. If I take the square root of 169, what would the answer be? 13. Not 13 squared, but 13. So basically, what's happening is this. Here's what's really happening. This number divides into that number. Two divided by 2 is what? 1. 5 one time is just 5. So that's what's really happening here with radicals. You can take this number here and divide each of the exponents. So we know this. We knew the square root of 16 was 4. These two cancel each other out. So it's just A four divided by 2 is 2. Whatever is here, we divide into there. Okay, let me show you that again. Let me do a bigger one here. That's a B. It's supposed to be a B. So B to the 18th, the square root of B to the 18th is what? What number is here? So what is 18 divided by 2? There's your answer. Okay, how would you do that then? So what number's inside this V? There's a 2. So that means I could take that 2 and divide each element by 2. 20 divided by 2 is 10. 30 divided by 2 and 4 divided by 2. There's your answer. It makes it much easier doing it that way. Because remember, the root tells you need, in this case, you need 2 of a kind to take it outside the radical. It has to be in pairs. What if we have that? An odd number. 3 is an odd number. Does 2 go inside 3? Well, it does, but we have a leftover. It doesn't go in there perfectly. So this becomes so it's A times A times A. Remember, how many of a kind do we need? Yeah, so once we have a pair, that pair goes out in front. Because there are 3 A's, if I have a pair, I can take it outside. So I have one A on front. So for every 2 inside here, 1 goes out in front. And we have 1 left over inside there. Let's do division. How many times does 2 go into 3? Once. So 1 times 2 is 2. 3 times 2 is 1. Remember doing division that way? Before you start using calculators? So this is called an improper fraction. Why is it improper? It's improper because the top number is bigger than the bottom number. Because usually when you use fractions, it has to be between 0 and 1, which means the bottom number is usually bigger than the top. So since the bottom number is smaller than the top, we know it goes in there 1 time with 1 left over 2. What is that called? It's called a mixed number. It's called a mixed number. Why is it called a mixed number? It has an integer and it has a fraction. It's mixed, but they mean the same thing. Now, how does this relate to what we're talking about in radicals? So we just worked this exponent out here. 3 over 2 is 1 1/2. This means that. If you ever have a mixed number as an exponent, you can take the base and split them up. You can take the base and split them up. So this A right here means this is a solid 1 on top of it, it goes out in front one time. Since this is a fraction, this A goes inside the square root. There's only one of them. Now, let's make that. Let's stay with this. How would you do that one? Remember, what does this number here represent? Remember, I can split these up into 2 separate ones. So what have you observed here? You see a connection? Look at these two here. What do you notice? They're the same thing. A radical can be rewritten as an exponent. It's fractional exponent. Okay, I went a little bit far. We're going to work back into this as this course goes on. But I'm showing you what we have now and what we can connect it to. So how would you do that? What's your first step? You could since there are 5 A's, I can do it this way. Everybody okay with that? How many of a kind do we need to take it out? Every pair inside there, one of them comes out. So there's that pair. There's another pair. And that one's by itself inside there. So the answer is A times A is A squared. Make sense, or am I losing everybody? I need to know because to me, this is trivial. I need to know what you think. Is it hard? Am I confusing you? Do I have to go back down and show you another way? What do you think? What's that? Anybody else agree? Okay, I'm moving forward. Do that one. Since you all thought that was easy, I can move on to the next topic. What's 27 made up of? Yeah, 27 itself, the number inside here is made up of 9 times 3. Okay, 3 is as far as we go. What is 9 made up of? 3 times 3. So 27 is actually 3 times 3 times 3. Remember, square root, once we have 2 of a kind, that 2 of a kind comes out in front. Whatever's left stays inside, and there's your answer. Okay, if there are any questions, now it's time to ask. So what did I do here? Since we start off with number 27, is it a perfect square? No. Perfect square is the 5 times 5, the 6 times 6, and some stuff, 7 times 7. So we take 27, we broke it down to its smallest pieces. What is it made up of? It's made up of 3 times 9. Can 9 be broken down? Yeah, 3 times 3. This is what's called prime factorization. Prime factorization. Here we take any number and break it down to its smallest pieces. Why prime? What does prime mean? Yeah, but not mathematics. That's in English, that's in literature, but not mathematics. Prime, when we talk about primes in mathematics, or very good, a prime number. Very good. Is any number that is only divisible by 1 or itself. Remember, every number is divisible by 1. So if a number cannot be separated, make the smaller numbers any further, then it's a prime number. So whenever you hear the word prime or prime number, we're talking about numbers that cannot be made any smaller. The opposite of prime numbers are composite numbers. any number that is made up of two or more factors of the number. So a composite number is just that. It's made up of multiple numbers. Is 6 a prime or a composite number? Well, the easiest way is, what is 6 made up of? 2 times 3. It's also made up of 1 times 6. So it has more than 2 factors. So it's a composite. The number 11 is a prime number because the only thing that fits into 11 is 1 times 11. It can't be separated any further. How about 13? Is 13 a prime number or composite? Thirteen is a prime number because the only thing that goes inside there is 1 times 13. It can't be broken down any further. All even numbers are composite numbers, except the number 2. 2 is a prime number. What goes into 2? 1 times 2. A prime number only has 2 factors, itself and the number 1. So tell me the prime numbers of 60. Is 60 a prime or a composite number? How do we know it's composite? It's even because it ends in a 0 or an even number. If it ends in a 0 or an even number, it's a composite. So what makes up 60? Yeah. 6 times 10. What is 6 made up of? 3 and 2. How about 10? 5 and 2. So the number 60 is made up of 2 times 2 times 3 times 5. It's made up of all these prime numbers. So a composite number has more than 2 prime numbers inside it. Can you think of a reason, an application for this process? Why do we have to find the prime numbers of any number? Division is the first example that you should think of. Whenever you're giving numbers, given any numbers, we did 60 already. We did that over here. So we know that's made up of 2 times 2 times 3 times 5. What's 240 made up of? Yeah, 24 and 10. If a number ever ends in 0, it's a multiple of 10. So we have 24 times 10. What's 24 made up of? 6 times 4. What's 6 made up of? And 4? How about 10? 3 times 5, yeah. So these numbers down here make up 240. We have 2 times 2 times 2 times 2 times 3 times 5. 3, 4, 5, 6. 1, 2, 3, 6. So we broke down 60 and we broke down 240. Now what do? Eliminate, right? Because whatever's on top and bottom can cancel. This 3 and this 3, this 5 and this 5. So our final answer is 1/4. This dividing line says that there's a top number and a bottom number. Has everything been removed from on top? No. Remember, every number has a 1 associated to it. If all the numbers are canceled, we have a 1 up there. So there's that 1. And on the bottom, we have 2 times 2 is 4. So that's one reason why I do prime factorization. So it helps us in fractions. How about with radicals? How can prime factorization work with factors, with rationals, radicals? What is 240 made up of? 2 times 2 times 2 times 2 times 3 times 5. Can anything come out? Is there a pair of anything? Yeah, there's a pair of 2s. It can come out. And another pair of 2s. It can come out. So we have 2 2s that go out in front. The 3 and 5 stay inside. So 2 times 2 is 4. 3 times 5 is 15. And there's your answer. Whatever you can take out from the radical, take it out. Whatever stays inside, stays inside. So the square root of 240 is 4 radical 15. Make sense? Again, all we're using is the same rules, which is now applying at different places. All right. All right. Is that proper or improper? Remember, a fraction is made up of the numerator over the denominator. For a proper fraction, the denominator is bigger than the numerator. So the bottom is bigger. Is the bottom bigger? Yes. So that's a proper fraction. And improper fractions is when the numerator is bigger than the denominator. That symbol means larger than. How about that one? Yeah, the top number is bigger than the bottom, so it's an improper fraction. Improper fractions convert to mixed numbers. And this is what a mixed number looks like. The integer is made up of the number of times the denominator fits into the numerator. That's the number of solid times it fits in there. Whatever's left over is your remainder. That goes on top of the fraction. And the bottom always remains the bottom. So the denominator stays there. It never changes. So how many times does 5 go into 13? 2 times. With how many left over? Over 5. Five goes into 13 2 times. 2 times 5 is 10. Remember, this is your denominator. This is the number of solid times it fits in there. And the remainder is your numerator. That's what this says. Whatever your denominator is, stays your denominator. The number of times it fits in there, solid, with whatever left over. Proper or improper? Improper, because top number is bigger. Since it's improper, we got to put it into a mixed number form. The only thing we know for sure is the denominator is 7. That's the only thing we know for sure. How many times is 7 going to 23? 7, 3 times. 3 times 7 is 21. So this top number is my coefficient. This number here is my remainder. Who needs review of fractions of dividing? Like it's called long division. Yeah, it's okay. We'll work on that. These both mean the same thing. This is where you have to remember your if you want me to, I can give you all a little small multiplication table. It'll help you until you memorize them again, like you did in elementary school. What's the closest number 8 fits into 75? How many times does 8 go into 75? Let's see. 8 times 5 is 45. It's bigger. 8 times 6 is what? That's 40. I'm sorry. It's 40. 8 times 7 is still too big. 8 times 8 is still too big. 8 times 9. 8 times 10. That's too big, so it has to be this one. So we know it fits in there 9 times. 9 times 8 is 72. Subtract them. You get 3. So remember, all you need are these 3 numbers. It's where they go that's important. The one on top goes by itself. The one out here, the denominator goes on the bottom. Whatever's left goes in there. Make sense? So that's pretty much how you convert from long division from impropers to mixed numbers. All right, do that, then we'll move on. Finished? If you got the answer of 3, you did it wrong. So let's see here. 3 goes into 76. Does 3 go into 7? How many times? Twice. So 3 times 2 is 6. Subtract them, I get 16. 3 goes into 16, how many times? 5 times 3 is 15. Subtract those. So this denominator goes right here. The 25 goes out in front. The remainder goes on top. We got that right. Now, if those of you messed it up, what'd you mess up on? This part? Because it's talking about the mistakes is more important than talking about who got it right. Let's see, if you got it wrong, where'd you get it wrong at? Or you just didn't try? One more or move on? One more. $341 divided by 7. So does 7 fit into 3? No. So does 7 fit into 34? Yeah. 7 times 5, that's too big. So it has to be 4 times. So 7 goes into 34 4 times. 7 times 4 is 28. I subtract them. Have to borrow a 10. 14 minus 8 is 6. Does 7 fit into 61? How many times? Yeah, so 7 times 8 is 'Subtract those. 11 minus 6 is 5. You keep on going till the remainder is less than the denominator. So we know the denominator is 7. The top number goes in front. And the bottom number down here is your remainder. That's your answer. Now let's go from mixed number to improper fractions. Let's go from mixed number to improper fractions. Here's the formula. We just have to do it backwards. There's the formula for conversion. Okay. Notice the bottom number will never change. It's always going to be the bottom number. So the only number it's going to change is the top number. 2 times 5 is what? Plus 3? 13 over 5. Which is what this thing says. A times C plus B. That all goes on top over the under. How about that one? Got it. Remember, the bottom number is always going to be 7, so that doesn't change. So what do you do first? 5 times 7, which is 35. 35 plus 2. There's your answer. So it's 5 times 7 plus 2 over 7. There's the process. Everybody okay with that? Simplify that one. Is it proper or improper? It's a proper fraction. The bottom number is bigger. So there's no converting to mixed number. Can we make it simpler? Yeah, so what is 18 made up of? 2 times 9. 2 is a prime number. 9 is made up of, so it's 2 times 3 times 3. That's 28. All right, it's 18, I mean. And 27 is made up of 9 times 3. 29 is 3 times 3. And those are all prime numbers. Can anything cancel? The 3s. The 3s. So I'm left with, there's my final answer. Can't go any further. Remember, this method is called prime factorization. We take the numbers and we break them down to its prime numbers. And then we cancel whatever is the same top and bottom. What do y'all think? Okay, let's take a break.